Okay, I think it's 5 past, so let's get started. Where we left off, when was it, Tuesday, we were just specifying directions, and so what we have here is a simple cubic example where we are now specifying the directions like this, where this is just the 0, 0, 1, and the 1, 1, 1 coming out at you. Is that kind of clear for everybody? Or, I mean, it looks pretty straightforward, but, and it is straightforward, but say, remember that we have defined the vector in direct space like this, MA1 plus NA2 plus OA3, where all of those are integers. So that points to a point in the real space lattice. So, you know, for the simple cubic, we just have the vectors A1, A2 in the y direction, and A3 in the z direction. So that, you know, when we are given this example, this direction here, what does it mean? The 0, 0, 1. It just means that we have m equals to n is 0, and we have the O being equal to 1. So you are just left with the direction being 1 in the A3 direction. It's pretty self-explanatory, but I just want that, you know, you kind of fully understand what it means there. Okay? Everybody good with that? All right, so let's move on. Kind of to sort of a new sort of area. Once we've defined the planes and the directions, what we are gearing up for here is to start a bit of scattering, and to see how scattering can enable us to determine the geometry of the crystal. Okay, so this gives you an idea in 3 dimensions, just diving straight in, and we'll work our way up to this, but this is basically the electronic band structure of diamond. Remember here for the FCC cell, we had the first Brillouin zone looked like that, and we had some high symmetry lines and points labeled on it. And this is showing you basically the energy of an electron in a solid as a function of the wave vector, its position in reciprocal space. This kind of plots are really important for condensed matter physics and tells you a lot about the material, okay? You don't need to worry about understanding it right now, but what is interesting is the lowest band here, it has a kind of parabolic shape, and you may remember from the free electron theory that we did, we saw the relationship between energy and K vector had that parabolic shape. E equals h bar squared k squared on 2m. Okay, so that has a shape similar. Of course, it's not a free electron material. Diamond is strongly covalently bonded, and we have energy gaps opening up at high symmetry points, and of course we have quite a significant band gap here. Okay, and so for diamond. Normally, these are all filled with electrons, so this is a valence band, okay? And then up here, these are the conduction bands, which are empty. So that's just to sort of show you where we are heading in, one particular. We'll get to that later on. But the important thing is just, this is the dispersion curve of energy in your crystal, and they look very similar to that. Different structures have different band structures, and so on. And this is called the effective mass, which again we'll get to a bit later on. Okay, remember when we were starting to talk about the reciprocal lattice, we mentioned that it can be thought of as a Fourier transform of the direct lattice points. So if we just consider this approach for a little while, and just one dimension, so we've got a one-dimensional row of points in real space that we can write as a delta function. We might call this a density. So there's a spike of density at these points. This is where your atoms are. So when you take the Fourier transform of this row of R, basically you'll end up with an expression here involving e to the I k a n. A is the real space spacing, remember? N is the integer, and k is the wave vector, which is equal to 2 pi n over a when it's a reciprocal lattice point. Okay? So if k, your reciprocal space vector, is equal to an integer multiple of 2 pi n a, that is, if it's a point of reciprocal lattice vector, then this exponential will just go to 1. If it's not a reciprocal lattice point, this exponential will go to 0. So we end up with this expression here for one dimension when we take the Fourier transform of just an array of delta functions. So expanding that into 2 or 3 dimensions, it has a similar form here, except we have d here, where d would be 2 for 2 dimensions, or 3 for 3 dimensions. And these now have, directions in three dimensions. So k being the x, y, z directions. Okay, so we have that. And what we are heading for is basically the structure factor. So go a bit further. Okay, in the crystal, we don't have exactly delta functions. Okay, we have an atom which has some kind of density, high density located at the origin of the atom. So later on, we'll consider that kind of thing. But here, this is just expanding out to 2 dimensions, as I mentioned before here. And if instead of the delta functions, we have electron density at the positions of the atoms, we can write it as rho of R, where R is a vector. And if our crystal is periodic with the repeating lattice vector of big R, where that's a vector that lands you at any other atomic position, then we have this relationship here. The density in the first unit cell will be the density of that atom in the second unit cell, third unit cell, and so on. Okay. So what we can do is, see, R at the moment is any vector position. Okay, it's not limited to being in the first unit cell. If now we say that the vector R has or can be written as the position of that atom, or a position in the first unit cell, x. So this is now a vector. It's nothing to do with the x direction, plus a translational vector r. Okay. Maybe I'll just draw that if it's a bit confusing. It's probably not confusing, but anyway, I'll put it up. So, yeah, what you've got here is you might have a number of unit cells, say just in 2 dimensions, and here's your origin. You might have a position vector r, and so what we are just saying is that this position can be written as the sum of a vector x within this unit cell plus a translational vector which has the periodicity of the cell. So this would be big R. So we have R being equal to X plus R. Okay. So, being happy with kind of that definition, now basically you can substitute in for the little r and bring out, for example, this term out the front, which doesn't depend on x. And so the integral becomes just over the unit cell, because this little x, remember, it was defined to be positioned within the first unit cell. Similar to before, what this boils down to, when you've taken this Fourier transform of the density instead of the delta function, it has a very similar form. We have, again, the d here represents the dimension. D is 1 for 1 dimension, 2 for 2 dimension, 3 for 3 dimension. This exponential term, remember, boiled down to a delta function such that k must equal a reciprocal lattice vector, otherwise it's 0. And we are calling this expression here S. So this is called the structure factor, S, and it's equal to this here. And we're going to do an example of that later on in the lecture today, and you'll get sort of familiar with the form of it. So basically we have, okay, here's the density. It might also be a scattering potential later on. And we will have the positions of the atoms within the unit cell and the k vector. Now this structure factor is very helpful in being able to determine the structure of your crystal. And for those of you that read ahead already, you'll see that we'll be able to determine not only the lattice constant of a material that you may not know, but also whether it's FCC or simple cubic or body-centered cubic. So the idea is, just for the moment, we're going to come back to that a little bit later on, in a way. So now we're just going to talk about diffraction in general. We're going to look at, Bragg's law, which you will know, probably 2d equals sine theta. And we're going to look at Laue construction and show that those two scattering formula are the same, basically. So, what is scattering? Basically, you can have some radiation incident on your crystal. There's lots of different experimental systems and infrastructure around the world where you can do these kind of experiments. And so you shine your radiation onto your sample, and then you will get back a diffraction pattern, basically. So by measuring the direction of the scattered beams and also the intensity, we can determine the crystal structure. Okay, so let's just back up a bit. Anybody ever wondered why X-rays are called X-rays? Yeah, I have. And apparently it's because when they were discovered a long time ago, they didn't really know what the nature of them was like, so they called them X-rays. So this is William Röntgen, and he got the Nobel Prize way back in 1901. So a little bit about X-rays. In the spectrum, everybody's sort of familiar with where they are. They are invisible, highly penetrating radiation, and they have quite short wavelengths here, 10 to the minus 8 to 10 to the minus 12. And if you compare that to the visible light range, about minus 10 to the minus 6 to 10 to the minus 8. Okay, so that's where we are considering, for the moment, X-rays. Okay, and because of their high energy, they're also quite easy to interpret. There's lots of different kinds of diffraction where you can determine information about the crystal. X-rays is probably the most straightforward because we consider kinematic scattering, the the wave function, or the wave just scatters once, and we have conservation of momentum and energy. Although we're not going to talk about it, there's also low energy electron diffraction. But in that case, we have that the scattered wave can scatter multiple times. And so its interpretation is a little bit more complicated. But there are lots of people working on programs and simulations that calculate these low energy electron diffraction, and they're pretty good, and they agree quite well with the experiment. So just to let you know, there's various forms of scattering, and also there is reflection high energy electron diffraction, which we'll touch at the very end, but not go into the theory of it. In that case, the radiation is shone at the sample at very grazing incidence, and your scattered waves look like sort of streaks. And this particular diffraction method is used for determining your surface structure. Okay? This is more for determining bulk material. Okay, so anyway, what we have here is basically we are using K to represent, for example, the incident wave vector of a plane wave, sort of sketched here, and then its scattered wave vector as K dash. And as I said, in this diffraction we have that the scattering is kinematic, so it just like scatters once and then off it goes out into your detector. What we have here is a conservation of the wave vector. We have the incident wave vector, okay, and the difference between that with the scattered wave vector is equal to a reciprocal lattice vector here. So that's vector diagram is illustrated schematically here, and this here is the diffraction plane. Okay. And okay, what does this show you? This shows you, for example, a setup. You have your X-ray source here, and it's shot onto your crystal, and you get a number of diffracted beams, which can look like that, for example. And you can measure where these spots are with respect to some origin, and you can also measure the intensity of them, and that will give you information also about the material. Yeah, it's a very big research area, and as you can imagine, we really do need to know the structure of materials, new materials, not just the ones that we know already. Okay, this is called the Awolt construction. Okay, it gives you some idea where to expect your scattered beams to be. Okay, this is called the Laue condition, that we have the difference between the scattered and incident wave vector being equal to G, a reciprocal lattice vector. So this is just in like 2 dimensions, but you can imagine it in 3 dimensions with the lattice coming out of you. The way that you proceed is you draw your wave vector that corresponds to your incident X-rays. For example, it has corresponding energy equivalent to this sort of magnitude of the K vector. And then you draw a circle around it. It's called the Awolt sphere. Okay, and then wherever it hits a reciprocal or a diffraction point, on your lattice, you will get a diffracted beam. Okay, so you can see that most of the circle doesn't actually intersect with a point, but at certain directions you will hit one of these reciprocal lattice points, and you will know that you'll expect to see a scattered beam on your detector corresponding to that condition. Okay, I think I showed before kind of schematically, but this is just drawn in another way here. If we have here the reciprocal lattice vector, G, then we have that there is a plane perpendicular to the reciprocal lattice vector, such that we have the incident wave vector and the scattered wave vector this vector summation here, and the plane cuts as shown there. Now, first of all, we just look at Bragg scattering. Remember, you'll probably all remember this from your earlier courses. So, this is a father and son team that got the Nobel Prize. I think the son was the youngest person ever to get a Nobel Prize at 25 years old, which is, I don't know if anyone will ever beat that, but that was pretty young. Okay, so what do we have here? This kind of indicates, here's your incident radiation, okay, coming in. These are crystal planes that the incident radiation is scattering off. Comes in at some angle theta, gets scattered out at some angle theta. So for constructive interference of these waves, we need that the path difference is equal to n lambda, okay? There's A, B, and this is the path difference between this wave and this wave here. So we have this condition here, and we can see that this is actually equal to d sine theta. This is also equal to d sine theta. So basically, you get your well-known condition n lambda equals 2d sine theta. Okay, so this is the Bragg condition for constructive interference. So important formula that probably you've seen before. Okay, so just a bit about X-ray diffraction. As I said before, they penetrate really deep into your crystal sample. So that's why they're used to determine the bulk structure. And the diffracted peak intensities that you get off are pretty sharp, as you saw in the slide earlier on. And that's helpful for analyzing the structure. So as I said before, the Laue condition and the Bragg condition, although they look different, remember the Laue condition was input, say incident wave vector minus scattered wave vector is equal to reciprocal lattice vector G, and the Bragg condition 2D equals sine theta, 2D, what was it, 2D lambda equals sine of theta. They look different, but so what we're going to do is show that they are actually the same. We are going to evaluate the structure factor for some examples, okay, and see how we can determine the crystal structure of one unknown material. Okay, so we're going back in a way. We're going to go back to the Fourier transform like we had at the very start and see the similarity here. Here, okay, this is a transition rate for particle scattering, which you'll know from your quantum mechanics, presumably. Incident wave, scattered wave, some potential here that scatters them. And we have the condition that it'll only be scattered if we have the Laue condition, the incident wave vector is equal in magnitude to the scattered wave vector. Okay, so what we do here is assume that we have a plane wave form for the incident wave and the scattered wave. So e to the I k dash dot r over here for the scattered wave, and for the incident wave over here. The L is just a normalization constant. Okay, so when you go through that, we end up with this expression here, which you can see is of exactly the same form as the Fourier transform. Okay, we have some factor out here, normalization constant, e to the I k minus k dash, just a g vector, like we had before. And here is, in this case, it's potential. Remember before we had an electron density, and right at the start we had a delta function. Okay, in this case, it's the crystal potential that the electrons are scattering off. Okay. Yes, I think we have said before that we're going to let little r, which is a position vector, be equal to r, which is a lattice vector, plus a vector just in the first unit cell. And we're going to get an expression for the structure factor. So what we might do is kind of just go over that together and see how that comes about. Okay, so it's to get a good feel of all of this stuff. It's it's good that you go and derive it yourself afterwards and make sure everything kind of makes sense. Okay, so let's just think about what we're doing here. Okay, so remember we have our periodic structure. Okay, we have an origin, we have some vector r, we have some vector x in the first cell, and we have some translational vector or lattice vector. Okay, so we're going to let r equal r plus x. And then, as I said before, r is a lattice vector, and x is the position in the unit cell. And we're going to make this probability matrix. We had this from before. Okay, so let's just rewrite that here, substituting in for r. Okay. And so what we know, because this is a periodic potential, we've got a crystal, right? We can just replace it with V of x, okay? And we can separate this out. And pull this part out of the integration because it doesn't depend on it. Okay, so it's kind of separated into two pieces. And this part here is a structure factor of your crystal. And we have, like before, that this exponential must vanish unless k dash minus k equals g, reciprocal lattice vector, which was the Laue condition. Okay, you can see that by like when you substitute in, g is 2 pi some integer n over a, your lattice constant. So, you know, when you stick that into the exponential, what is that? So r was just a vector, which you can say in one dimension, if you like. Same for 3 dimensions, is just some integer times the lattice constant in real space. So these will go out. This is just an integer. So basically that will, the sign will go to 0, right? Because you'll have cos of 2 pi, what is that? Some integer, n times n, let's call it O, minus I sine of 2 pi O, where O is an integer. So that guy will go out, and you'll just be left with the 1 there. Okay. So it's this part here, this structure factor, that is going to allow us to solve things. Okay, so just remember for now the structure factor, and we're going to come back to that later in the lecture. We're just going to sidestep a little bit and show how the Lowry condition is the same as the Bragg condition. Just a little kind of proof. You won't need to know how to do the proof, but it's good to see that these two conditions are actually the same thing. Okay, so I'll get rid of that. Basically, that's just summarized what we did, like on the board. It's just ending up with your structure factor there. Okay. So this is how to show that the Lowry condition and the Bragg condition are the same. Basically, we're going to start off with the Lowry condition and get down to the Bragg condition. So, okay, this is kind of the setup that you've got. You've got an incident wave coming in and a scattered wave going out. You have an interplanar separation D. D is given by 2 pi on G. Now, you might look at that and think, hey, where did that come from? But remember a lecture or two ago, we got an expression for D. Remember, it was something like, what was it? 1 on D squared. What was it equal to? Anyway, it's in your lecture notes. So basically, if you can prove to yourself that this is indeed correct, okay? So what you do is you go to that D equals, I think it's 1 on D squared equals A over the square root of H squared plus K squared plus L squared. Remember that? If you substitute that in here, you'll be able to work that out. Anybody have trouble getting that equation, just email me, okay? You'll be fine. So, okay, so we have this situation here, and from geometry you can just see that the dot product of K with G, where these got hats on, so they're just unit vectors, is sine of theta, and the same thing for the reflected wave vector, and its opposite sign. Okay, here. Now we can rewrite this expression in terms of hats by putting the wave vector equals 2 pi on lambda, which is the wavelength of the incident radiation. These now got hats on, just coming straight from here. And then if you make the dot product with another g hat, which is in the direction shown here, then obviously it equals g hat dot g. continue. Okay, this is what we had before. And from the symmetry and the angles defined in that previous picture, we can get this expression here involving the sine. So that's how the sine gets involved. That from that picture we had before, and working out G dot with K. And basically you can see that it leads you to the Bragg condition. Okay? So, you know, the Bragg condition has n in there, where n is an integer. If you do the same working here, instead of with G, but with NG, because NG is also a reciprocal lattice vector, then you can get your n into the equation there. Okay. So when you hear about the Lowry condition and the Bragg condition, you just know that they're basically the same things. Okay, so what about the scattering factor and how can it help us? Remember we had derived that expression there. So just another important thing is to say that the intensity of your diffracted beam that corresponds to a particular reciprocal lattice point or plane is equal to the structure factor squared. Okay, so when one is trying to analyze the diffraction data, we know that the intensity of the spot, which you can measure, is proportional to the structure factor squared. So the structure factor is really important quantity. Now, just to step aside a little bit to talk about neutrons and X-rays here. Neutrons, you know, we can do neutron scattering and we can do X-ray scattering, as well as other scatterings that I mentioned before. But for neutron scattering, they scatter from the nuclei, and the scattering potential is short-ranged here. You can approximate the potential, V, in the unit cell, X, for any position vector X, as being equal to some f of j, which is called a form factor, and it represents the scattering strength. And the form factor, these are terminologies that you can know and remember in terms of the scattering theory. And so for nuclear scattering, the atomic form factor is proportional to something called the nuclear scattering length B of J. So for neutron scattering, you can approximate the potential to be a delta function, where you have the nuclear scattering strength located at the position of the atoms, the nucleus and the atoms. Okay? So that's sort of what you can use for the potential for neutrons. Okay, and when you substitute this V into the expression for the structure factor earlier, then we get this kind of thing, but with the B of J there instead. Okay, and then we're going to look at the X-rays and see how they are slightly different. For X-rays, the potential is taken as being proportional to the electron density. Okay, so the X-rays scatter off the atoms, and they feel like the core electrons. They penetrate not just from the valence electrons, but for the whole core electrons as well. So you can approximate the potential for X-ray scattering as being equal to the atomic number Z, which tells how many electrons you've got, and some short-range function there. But it kind of has a similar form, and it's located at the position of the atoms J in your unit cell. And so when you put that expression for V in, you get the structure factor with the form here, and F again is the form factor. And for people that actually calculate these kind of things as part of their research, you know, there are well-known form factors that you use for particular atomic species. So something that people can figure out. Okay, so just a little bit about the difference between neutron scattering and X-ray scattering. Neutrons are really good for detecting hydrogen. So if you've got a material that's got a lot of hydrogen atoms in it, they can detect that really well. The hydrogen atoms are very light, and X-ray scattering has trouble detecting the presence of the hydrogen atoms. Yes, and the thing with X-rays is the advantage of X-rays. One, there's many more X-ray facilities around the world than neutron scattering facilities. But two, X-rays, you do need a very small sample size, which is not the case for neutron scattering. And, you know, we have a really good neutron scattering source here in Australia, in Sydney, down at ANSTO. And some people, you know, do their research down there at ANSTO, and some students have been working there as well. Okay, so let's do an example, okay? So what do we know, and what have we got here? We know that the intensity is proportional to the structure factor squared. We know, well, the structure has a form like that. We're going to do this example, and I'm going to do it slowly with you, so you, well, how does that come about? I'm sure you can figure it out, but let's just do it together. We're going to look at cesium chloride, which has the structure here. You can think of it as a cubic structure with cesium at position 0, 0, 0. Here, the square brackets represent position of the atom, not direction, okay? So cesium is at position, the origin, basically, and the other atom, chlorine, is right in the center, half, half, half. And so we're going to obtain an expression like that. But let's just do it slowly together. Let me see. So, first of all, you know, we have our cell. It's always good to draw your cell. Got an atom here, something like that. We have, from before, the structure factor for some HKL is equal to the sum over J, where J are the number of atoms in your unit cell, the number of basis atoms, if you like, equal to some form factor, F, e to the I, G dot X of J. Remember, X is a position vector. It doesn't mean the X direction here. So we know that our reciprocal lattice vector can be written as H B1 plus K B2 plus L B3. Remember, they're just integers. It doesn't matter whether you use MNO, HKL, whatever. So an X of J is, say, the X coordinate of atom J lattice vector. Let's say this is A1. And then we have Y of atom J, A2, plus Z of atom J, A3. Okay. And then, okay, so we want to make the dot product of these guys. G dot X of J, we just get H B1 dot with X J A1, K B J plus J, Y of J A2. And then plus L B3 dotted with Z of J, A3. Okay. So why is that? You know why that is? Because we have there's a delta function there. So we have G dot x of j equals to 2 pi h x of j plus k y of j plus L z of j. Okay, that's what was written at the top of the slide, but that's just obviously going through how you actually get that, which I'm sure you could have done yourself, but there it is. So now we want to work out the structure factor, HKL, sum of J, form factor of atom J, e to the 2 pi I hx of j plus ky of j, L of z of j. So you know that we have a cesium atom at 0, 0, 0, and we have the chlorine atom at aeon 2, aeon 2, aeon 2. So that's the J we have to sum over, okay? So first, what we have to do is substitute in the positions of the cesium atom into here, here, and here, okay? So we end up with F, cesium, subscript cesium, say, e to the 2 pi I 0 plus F of chlorine, e to the 2 pi I h a half plus k a half plus L a half. So you can see that these 2's will go out with that 2. So you will end up with cesium, because that will go to 1, plus F of chlorine, e to the pi I h plus k plus L. And these will be an integer, okay? So whenever you have, like you know, e to the I pi n, the signs will all drop out. So we'll just be left with F of chlorine cosine of pi h plus k plus L, which you can write as minus 1 h plus k plus L. Okay, so what does that tell us? It tells us that it doesn't really matter. We can have any value of h, k, and L, and we will get a non-zero answer. Okay, so basically for this structure, any h, k, and L should give us a diffracted beam, because this will be non-zero. Okay, so these h, k, and L, I mean, from this, we're going to see that selection rules will develop. Next time we will look at the body-centered cubic and the face-centered cubic structure, and we will see that you will get certain values of h, k, L will produce no diffracted beam at all. And this will be a way which you can tell what structure you've got. Okay, so I think for the moment we'll just leave it here and we'll continue on with this later on. Yes?
Sorry, what happens to the A?
Oh, the A. I think it drops out because we are defining the positions in terms of the A vectors. So we are just looking for the coefficients of the A vectors, I believe. Oh, and yeah, they just don't enter. Let me double check that. Yeah, the A, remember we have A dot B, AI dot BJ equals 2 pi delta function. So, yeah, the A has, the A1, A2, A3 are actually written in terms of the lattice vector, okay? So let's come here. So A1 is actually equal to AX hat, if you like. Okay. Thank you. We better finish here, I think. Any questions? Always just email me. Feel free to talk to me. It's fine. Yes. Oh, hello. I remember you from what? Yes.
Yeah, I missed the first couple when I was sick.
Ah, that's okay. Yeah.
But, this is a bit of a long-winded question. In the Derby lab,
Right.
I did expose powdered fraction on some quartz.
Okay.
But I was struggling because I know it's a tetragonal hexagonal crystal structure.
Okay. This is a 30 level. Yeah, I'm decoupled from what you were doing in the
Yeah.
lab. Yeah. So.
I finished the experiment, but this is for writing a report. I just wasn't sure how you actually go about finding the HK and L values for hexagon.
Okay. I'm not sure whether we'll actually get to that or not.
I might ask you later.
Yeah, that would be good.
Because
Yeah.
I asked Dalton about it and he doesn't. He doesn't.
Oh, good. Is he?
He was last semester, but this semester he's I think he's teaching.
Yeah, that's right.
So Marek, he actually was quite excited with it. So
Yeah. Yeah.
thank you.
Okay.